All right, cool.
Okay, hi everyone, welcome to this Haskell Z meetup. I'm going to talk a bit about Haskell mistakes I've made in the past. I'm Jasper, I really like Haskell. I've been writing Haskell for a long time now. First through like open source projects and university projects, and then I've been fortunate enough to work professionally with Haskell for a few years now. And so during this time I've made a lot of obvious mistakes, and I'm going to try to teach you some techniques so that you don't make the same mistakes as I do. So this talk is mostly about what I call beginner mistakes, because if you know how to avoid them, you probably can avoid them, although like as an intermediate programmer you can also encounter them, and sort of like some signs that can tell you if your Haskell code is a bit smelly, as we say. I'm not going to talk about like the very basic mistakes, so I'm not going to touch on like parser errors or like type errors. Otherwise, this would probably be like the number one most common mistake, like putting the equal sign in the fib function there. Okay, but first I'm going to give like a bit of a more general introduction in avoiding these mistakes and nasty code. So for most teams in the world, like it's not possible to have like a perfectly clean, perfectly tested, perfectly documented code base. Since we're all like, since we have like finite resources, we have finite team members, we have finite time, finite money. So you sort of like have to choose where you put your focus, right? I mean, like if I, for example, write like a very small project and I put like a lot of time in it, I can have it like perfectly working and like what I would consider like perfectly clean. But as soon as you're like doing like some commercial development or larger medium-scale projects, it just isn't possible anymore. So you need to sort of like choose where you put your effort. There's a few choices you can make, a few trade-offs. Like you can, for example, make sure every sort of like line of code looks perfect, like between 80 columns. There's no like all your variable names are named correctly. You can put like a lot of effort into that. I think you can put like hours and hours into just naming alone if you want. Or do you need to get the job done? You have to write some code. It has to work by tomorrow. You don't really have a choice. Or it needs to work super fast, and like you can't afford to have like these nice abstractions simply because they have like some runtime overhead. So yeah, sometimes we have to make these decisions, and what usually works really good for me is focusing on like the module, like a Haskell module, as a sort of a unit, and considering like sort of like the module from outside, and sort of like from the outside, the module should be more or less clean. That's usually sort of like the trade-off I try to make if I have finite time. So what does that mean? Like if you have a module, the sort of like the expose interface, like the functions, the data structures that exposes, these should be like relatively clean, and like you shouldn't have to do like all these like nasty, unsafe perform IO tricks to get it working. Inside the module is free to do whatever it wants, as long as you don't sort of like kind of if you can't absorb like the effects from the outside. Then it's usually pretty nice to work with that module. And the same for documentation. Like if you have finite time, it's often like impossible to sort of like document every top level function, like every parameter, every data structure. But in that case, I try to sort of like document every module. So like if you open up the module file, of course the module shouldn't be like too long, but there should be like a quick introduction about like what the module is for, how you use it. And then usually you can infer the rest from the names of the function and the data types. I mean, if it's not that clear, you should obviously document them. This talk is going to be very, very subjective in these a couple of these topics. And the same for testing. You should have like a few tests that verify that the whole module sort of like works correctly as a unit, but like maybe you don't have to time to test like every internal function 100%. Okay, so with that sort of like out of the way, let's start with like the first mistake. So GSC doesn't compile with all warnings enabled by default, and this is a bit of a problem because there's like a few warnings you really want to get. Like if otherwise you wouldn't be using Haskell if you don't care about like the compiler telling you nice things. So always compile with wall and like use an error for if you want to run it in production or if you want to run tests, then you will immediately know that something is fishy in my code. A lot of the warnings in like wall are like what I call like low risk. Like I don't even know fully what some of these do. I went through all of them and sort of like sorted them by what I consider like low risk, high risk. But like these, I mean, like if you have like a few unused imports, for example, like your application isn't going to break, right? So maybe you don't really care about these. But then there's also like some medium risk ones. Like for example, if you have like unused binds in monadic code, it can sort of like mean this function is like suddenly returning another result type, and you want to be informed of that by your compiler, or you want to sort of like explicitly say, I don't care about the result. It's unused matches and like orphans. It's sort of like, it's not immediately going to tear down your application. Unlike the high-risk ones, there's a few like high-risk ones which will actually just like produce runtime errors. If you ignore these warnings, you run your code, you get a runtime warning. Yeah, so first mistake, always compilable or never compilable.
Where would you put the warning on unused variables?
That's medium risk, I put it.
Oh,
Unused matches.
Like,
because like it's a bit, yeah, I was first going to put it with like low risk, but like sometimes it's sort of like, if you have like functions, calling functions, and you don't have this warning, and you often have like these like parameters which you pass through to a function, which gets passed to another function, but actually you're never using them, right? And with this warning, I find it often sort of helps me to trim dependencies of the functions, if that makes sense.
For me, I mean, my experience is that if I have a parameter, for example, with a function that is not used, it's a very strong indicator that I either forgot to do something in the function, so I took the parameter, or it's not used. And I would even put that on high risk actually, because
it's almost always a bug.
Yeah.
Yes.
Yeah, and also like if you're actually not using it, it's very easy to sort of like prefix it with an underscore if you think you might need it in the future. Okay. Yeah. So let's look at the next one. Wildcard pattern matches, a great pet peeve of Simon. Let's start with an example. If you have like a data type, for example, we're writing some business logic for a prison here. Someone can either be a murderer or innocent, and then you have some code dealing with releasing of prisoners. If you're innocent, you can be released. If you're a murderer, you stay in prison. I'm using a syntax extension here, which we'll talk about a bit later, but the intent of the function is pretty clear. So the problem is, if you have wildcard pattern matches, you can write functions like these, right? Like you want to send someone to the fire squad. I mean, like it depends what country you're living in, I suppose. And if the person is innocent, you don't want to send them to the fire squad, of course, but otherwise, yeah, let's go out with them. And this sort of function, which relies on these wildcard pattern matches on your own data types, they're very fragile. Because if you extend this murder data type later, like you're pretty sure they're a murderer, but like it's not completely been decided yet, then this function will just continue to compile without warnings, even if you're not using, you're always without warnings, like there's no way to warn against this. Here you would get a warning if you're compiling with WAL, so that's a good thing, because then you know okay, what do I want to do in this case? But if you have like a lot of code like this, it's very, very fragile. Because like if you only have these 2 or 3 functions in a file, it's easily visible when you extend the data type, but as soon as you sort of like have like a 400 line module, it's easy to forget a function. And like wildcard pattern matches isn't really the only sort of form this can occur in. Like you could also like encounter the same thing where you're sort of like using the equality instance. That's just the same result, and I think this is sort of like a symptom of like another thing. Like in this case, like you sort of like rely on the internal structure too much, and you should try to hide the structure in that case and sort of like use these predicates on it instead. Of course, like this isn't always like a bad thing if you're getting like a maybe, an either, a list. Like it's very unlikely these will ever be extended. So in those cases, it's definitely fine to do. But otherwise, it's best to always like explicitly match. Like there's some annoyance involved sometimes. Like if you want to have like 5 cases and you want to do the same thing in the last 4 cases. But even then, it's often easy to sort of like add like a where clause where you sort of like specify what you want to do in these 4 last cases and then use the where clause 4 times.
Excuse me?
Yeah.
While I agree with regarding the safety, I was wondering regarding runtime, is there some significant penalty for listing all the patterns, especially if it's sometimes large? Maybe the catch-all is much faster or something. Do you have some insight there?
Yeah, it does incur, like I would say it incurs runtime overhead. Like unless the compiler is, if Thomas agrees with me, I'm probably right. But unless GC is much more than I thought it would. But yeah, like of course, like what I said in the beginning, like sometimes you have to sacrifice like clean code in order to get performance.
I was just wondering which range of categories overhead is. Do you think it's significant, or do you think it's usually in the general?
Well, like it depends where the code is. Like if it causes like a branch misprediction in like a very tight loop, then it would have like some overhead. It really depends, right?
It basically does binary branches.
Yeah.
And I don't know if you have a lot of cases, then it might use a lookup table, in which case it's basically the same cost. Well, actually, it depends, but let's say a few branches is the cost.
Yeah.
And a bit more code size.
And slightly bigger code,
yeah. But yeah, it depends if it's on the critical path. You could look into making it faster. Otherwise, I think this is fine. Okay, next mistake. I make this mistake a lot, especially if you come from like another programming languages where exceptions behaves differently than in Haskell. There's 2 forms of this mistake. So the first one is like the beginner form, and then there's the advanced form. Like you sort of like you think you know you understand exceptions, but like you sort of falsely assume, yeah, I understand exceptions. Whenever I write some code, I will take it into account, because you don't do that. So yeah, let's start with this piece of code, which is like relatively easy to see. So like you have this try, which is sort of like which is supposed to catch errors. You return a list which throws an error in the 3rd element, and then you check if it's if you have the error or if it's the okay case. If you have the error, you print the error. So who thinks this will get in the left case? Okay, so everyone is right, because this triggers the 2nd case because of the laziness in the list. It's only what will happen is you will actually start printing this. You will get like 1, 2, and then you will get the error. But yeah, this is already like not easy to see if you have like a try around the. Let's look at this one. Does this fix it, you think? Yeah, this doesn't really fix anything because the throw is still lazy. The only thing you could do here is move the throw up or use throw IO. But the point here is that it's very easy to make mistakes, especially if...
Actually, if you move the throw to the top,
then
there's also a problem, because from the compiler's point of view, this is the same as undefined, which means the compiler feels like it has the freedom to rewrite this to some other exception. So if, in this case, you're catching all exceptions, but if you only catch specific exceptions, it may not actually catch it because the compiler decided to rewrite it.
Yeah, like I think the idea is that you should always use throw IO if you're doing IO.
But you should never use try because it captures async exceptions.
Yeah, exactly. Well, not with some exception anyway. Oh yeah. Because you can. It depends what sort of like type you give. Right? So it's a bit tricky. And it gets even trickier because, as Simon said, you have like asynchronous exceptions, and like this is just like very, very hard to reason about it. Like you have this foo function which does something to a socket and then returns the result, right? And the way you write this is you first open the socket. You have your function f here, which you use to do something with the socket, and because you have this try, then you close the socket. So, I mean, intuitively, if you just see this, it's very easy to assume like the socket will always be properly closed, right? But most people here hopefully know that this is not the case, because like the problem here is that so open socket can actually, for example, return a proper socket, but then you have like asynchronous exceptions which can arrive from another thread. For example, like another thread decides to kill this thread, and in that case the exception can sort of like arrive in between those two statements, so after the socket is opened, but before like the try handler here is installed, and in that case you leak the resource. There's a few patterns for fixing this. Like for example, mask. Mask allows you to sort of like mask your own thread context from like asynchronous exceptions, and then you get restore to restore them again. So what happens here, if you have like some sort of like another thread sends like a timeout, it can't arrive here because we're masked. It will happen like inside the restore. So hopefully this would work. Do you think there's still like an error in this?
Aren't we masked when the closed socket is running?
Sorry?
What happens if closed socket throws an exception?
Yeah, then the exception would trickle out, but like the socket would be closed, right?
Okay.
But there's actually still a problem here, because we imagine that f is like a lazy function, which sort of like does lazy IO, reads a bit from the socket, but then uses like unsave enter leave IO to return like a temporary result. So R is maybe like an infinite list. Then we still have a problem here. So we would need to sort of like use some of the, like the DeepSec boilerplate to fully evaluate R, which is not fun. So I guess the gist of it is this is all like very, very hard to reason about. So don't do any of these two. And this is like the sort of like the debugging pattern you encounter when you're like dealing with these exceptions, especially you have like if the exception is like thrown by a third-party library, and you don't really know what it is doing. It has some documentation, but since you can't see these exceptions in like in the types, you don't really know anything about it. And then, yeah, it also depends like what context the thread is in. So there are like a few patterns that can sort of like remove the pain a bit. So the first one is always using pure code where possible. There's a bit more about that later. So this already helps a bit, because at least in pure code you don't have to reason about like asynchronous exceptions that much. Then a second one is avoiding to throw exceptions from pure code. That also helps because it avoids like this clause of errors where you have like this whole thunk or lazy structure, but the error is sort of like hidden deep within, and you only see it much later. So this is also a big help. And then the last one is to use like more predictable, what I call them, monad stacks. In these cases, you still have to deal with like all the sort of exceptions from libraries you use. But if you use like this type, and obviously like E shouldn't be like the sort of like the exception we saw before. It should be like your own, just like a normal data type. Then you can usually avoid some of the madness by not sort of like adding your own exceptions to it to make it even harder, or like use asynchronous exceptions to sort of like pass messages between threads, which is also something you can do in Haskell if you want to. Yeah, so these things already help, and there are a few like existing solutions like resource T, especially. I think there's resource pool. These are like two sort of like libraries which help you managing these resources. There's bracket, which is like a pattern for doing this like in the sort of like the best possible way. There's still some things that can bite you, but like if you stick to these existing solutions, you know where these sort of like problems can occur, like whenever you're dealing with resources especially, then you should usually be good.
What do you think about Gabriel Gonzalez managed library? I view it sort of as the smaller brother of resource T.
Yeah, it could be in this list. Yeah, and in fact, yeah, I also like, but it's like a wraparound, like with functions.
It's essentially bracket, but wrapped nicely such that you don't have to care about it anymore. Yeah. And if your allocation pattern is purely stack based, it just works. Resource T is a big hammer for if you just use stack based allocation.
It's a bit more general, I suppose, but I assume you can use managed most of the time.
That was my experience that I made, but
So let's talk a bit about another mistake I made. For a long time, I think I was trying to avoid like writing any code that relies on JC extensions. I guess because like before I was coding Haskell, I was doing like some C and C++, and like for those languages, there are a lot of different compilers. They each have their quirks, and I guess it was sort of like used to like you should always like write portable code. Don't rely on these different compiler tricks. But like this is entirely untrue for Haskell. If you think if you're talking about like production quality compilers, there's only JC. The rest, and even like the other main compiler, UHC, supports most of the extensions. Then the extensions are like widely used in like the sort of like probably most dependencies you rely on. So if you would decide to port your application to some other compiler, you would have to start with porting all your dependencies anyway. And also, yeah, it's Haskell, so refactoring is, if you decide not to use some extension, you can usually refactor the code pretty quickly because you have the help from the type system and the compiler. Let's look at some extensions. Yeah, so I run like a script which counts the number of extensions per file, like on a number of like production code bases I've worked on. And surprisingly, the number was almost exactly the same everywhere, like around 3, which is surprising because it was like written by like widely different authors, and these were like the most commonly used extensions. So overloaded strings, template Haskell, derived data typeable. Like these are all like very safe things to do, and like if you try to avoid these extensions, you're just sort of like imposing pain on yourself and forcing yourself to write more code than strictly necessary. So these are a list of viable extensions, and there's a bunch of extensions that sort of improve readability. Like often if you sort of like you have some experience writing Haskell, but you don't know that much about like the different language extensions, and you're trying to write some like nasty pattern matching, and like, but in this case I also want to check that. Like there's often like extensions that help you, like for example view patterns and pattern guards are very useful, multi-rate if. Like my current opinion is that all sort of extensions which operate like purely on like syntax are always sort of like whitelisted for usage.
Doesn't view patterns and pattern guards conflict a bit with the rule on being complete with respect to pattern matches? Because they sort of...
Yeah, because you can, but like it depends, like if you have like partial functions in your view patterns.
I would just think that if you have a pattern guard that grabs one pattern out, but then the rest falls through on other cases, then you actually need to rely on some default cases, even. Such that
so it's not always a good idea, of course, but like they're very useful if you're, for example, like matching. Like I use pattern guards, for example, a lot. Like if you have some case and then you want to look up something in a map and it has to be there, for example, because then you can sort of like match the case and then you say, oh, I want to catch like a just here. So for those sort of like improving the cleanliness of the code, it's often like a nice thing.
Okay, cool. What does binary literals do?
It basically means that you, instead of writing like 0x and then FA for like a hexadecimal, you also have 0b for writing integer literals. It's pretty useful. Like I was writing like some protocol buffer code recently, and then you have like a lot of binary things you want to test if you want to test your encoding, and otherwise you sort of like write the hexadecimal number in your code, and then you sort of like write in a comment like the binary form, and this allows you to avoid that. I realized what's missing in my slides is actually like a list of blacklisted extensions that might be more useful. Yeah, but like there's also like a bunch of extensions which sort of like write code for you. Those are all like super useful, especially like the first 3 I use all the time these days. Also, I'm a big fan of record wildcards and like derived generic. So I don't think I have enough time to go through each extension individually, but the big message is like use them as much as you want. I think the only hard blacklisted thing, in my opinion, is sort of implicit parameters. I really don't like that extension.
In predicative types?
Yeah.
The predicative types.
Predicative types.
So you could have a list of for all A to A's.
What about rank n types?
I'm fine with them.
Sometimes you need them.
Yeah, but like usually you can just use rank 2 types. I mean, there's a few cases where you need the.
What about concurrent instances?
Yeah, that's also on the blacklist, I think.
Yes.
On the dark.
But I don't think like they used to be. I don't think you need incoherent instances that much anymore, since like in the recent GDC versions you have like all the new type class goodness. Like you can make like these closed type classes, and I think that those solve like a lot of the cases where you could have considered like incoherent instances in the past. Yeah, but what would be useful here is a blacklist. there's like a series of blog posts about these extensions, which is very, very nice to read through if you haven't heard about it. Like it's very nice to learn new ways to write Haskell. Next mistake. I've made a lot. Like this seems to be like the mantra in some Haskell teams, but it's not really true. Like the type system gives you a lot of like safety and like guarantees about what is going to happen, and like if you use Haskell too much and you're always used to sort of like, okay, this seems to compile, you test it, it works. Like there's a real danger of like that after a while you're sort of like, oh, it compiles, okay, maybe I can skip the test and it will probably work because it always does. So this is a real danger. And then the second problem is like if you sort of like Google for like testing libraries or like testing documentation patterns in Haskell, a lot of the things you end up with is these sort of like talks about like quick check and small check, which sort of like very clearly show you how to test like these pure functions, or like how to show like properties, or like even use equational reasoning to prove like some functions. Yeah, there's sort of like a big focus on that, and that's a bit of a problem because in the end, what really matters is not like if your sorting function is correct, but the end result is important, right? If your application compiles a binary, or if your application returns like a valid HTTP response. So I think a big mistake I've made there is sort of like having a lot of sort of like different small quick check or HUnit tests, which sort of like test different functions throughout different modules, but not focusing enough on like testing that the whole thing works. And I think the situation is getting better. There's like some things which help you with that, some packages like some that help you to test like a snap interface, or like even web drivers, so you can sort of like automate a browser to like click on things and like submit text fields. So that's also very useful. Tasty golden test, something which I haven't heard about like until recently, is basically you run a test and you have like some expected output files. And so you run your entire application and you look at the actual output files, and they should all be the same. It's also a very, very nice way of sort of like making sure that the whole thing works.
The GHC test suite is basically
exactly.
Kind of test, right?
Yeah, this is very useful to test compilers, but like in a lot of other applications, it's hard to apply.
Does Tasty Golden have support for like normalizing things, or if the output contains timestamps or something?
No, that's very like in the golden tests for like an application I'm working on right now. Like sometimes they produce like sometimes a test, so it's a compiler. So sometimes you have like some code and you want it to produce like an error message, like a nice looking error message, and then there's like. In the error messages, usually it's like the path of the file you were compiling, because it will say like, in this file, in this thing, you have this error, but then of course in Windows you have all the backslashes. So it often, like, it's not a perfect solution. You often have to sort of like do some substitutions depending on what you're looking for, which is like still a bit nasty, but like it's not that hard to use, so it's usually worth it.
There is a new pretty printing with annotations library, right? Probably saw that.
Yeah.
So maybe for this kind of stuff you could have specialized pretty printers which can leave out the tricky stuff.
Yeah. Or like compare like the structure for equality instead of the output here. But then you wouldn't be testing the whole application from the outside again. So it's a trade-off, I guess. Like even if you don't do it in Haskell, there's plenty of other ways to test everything. You can roll your own framework in Haskell, or you can use Bash or Python or JavaScript, or whatever you want. Like, the important thing is to just test it. It doesn't matter with what. Alright. Another easy mistake to make in Haskell is like wrong use of string types. Like this is me like some time ago. Like, you write some code, you use the Haskell string type because it's what all the tutorials use. You find some really so it's very slow. You wonder how. It uses string very intensively. You find this Stack Overflow thread. It tells you, yeah, string is very slow. Use byte string instead. And then your output is something like this, and you're wondering, yeah, like, what was going on here? That's a very common mistake to make. And this is the solution, basically, what you should use. So if it's binary, you should use byte string. I think a lot of the confusion stems from the fact that byte string is called byte string, where I think just like bytes would be a better name. Then there would be less people thinking it's some sort of string. The second question, so if it's not binary but human readable text, then the question is, are you writing hello world? If you're writing hello world, you can use string, but otherwise it's probably safer to use text. The text library in 99% of cases. It's a bit more complicated than this, because like both byte string and text have like lazy and strict versions. So here's a second decision tree. If it fits in memory, you can probably use strict. Otherwise, if you're doing like a single pass over the data, like some sort of like stream processing or anything like that, the question is, do you like really understand lazy I/O, which is implemented using unsaved into leave I/O. Like, there's a lot of sort of like subtle things that can sort of like stab you in the back when you least expect it. So I reckon in most cases you want to use pipe or conduit for sort of like lazy text or lazy bytes things, where you have some sort of stream. Otherwise you're of course free to use lazy I/O. Then if you're not doing a single pass over the data, you probably want to use a database, or like use some mmap or like fseek or whatever you want. But I think like most of the time you want to use conduit or pipes if your data doesn't fit in memory. Next mistake, not using enough pure code. So especially in the beginning, it's easy to write code like this. You're writing some application, you want to read two numbers and then do something to them, like whistling them, and then print that. This is very easy to write, and it's also very easy to take out the pure code, right? Which is something Haskellers often say you should do. So in this case it's super trivial, the pure code happens here. You take it out, you put it in a function that sort of has the inputs and the outputs without I/O, and then you have like sort of like an I/O wrapper around it which interacts with the real world. You read your input, you call your pure code, and you print it again. So this, and I think this actually, this is a super common pattern, and like it actually also works for like much bigger applications. Like for example, this sort of like very simple pattern even works for a compiler, which is probably one of the more complex sorts of applications. So this is the easy mode, right? The problem, however, like it's not always that easy to sort of like separate your pure code from your code which has to deal with I/O. For example, the easy case where it's not always possible, like you have like some 16 gigabyte text file, you don't want to just read it in and then I don't know, do something with it, or like you need to do some I/O first before you can decide what happens next, or there's like multiple threads, all these sort of like more real world applications, as we call them. But like we're going to look at an example of where it's much harder to do this sort of like taking out the pure code, and sort of like step through that, and like I hope we'll see that it's almost always like possible, and like it improves like the structure of the application. So this is like if for example we're writing like a very simple sort of like web server. There's usually like very straightforward ways to also take out the pure code here. Like for example, you could say like you have this request thing, and you have like a response thing, and then your application is really just a function of request to response, right?
Shouldn't that be a byte string?
Well, it's
There's
actually
no hello in there.
It's actually Unicode, right? So it should be text.
I'm not sure.
It depends.
HTTP
Yeah,
standard
depends.
doesn't say it's a
say,
Unicode
yeah.
response.
Yeah. But we're in the case where we're writing hello world, so it's fine.
It's a web hello world.
Yeah. Okay, and so like this would be the version where you don't separate your sort of like pure code from your IO code. You read the request, you look at the path. If it's like index, you send some 200 back, otherwise you send 400 back. Also using wildcard pattern matches here, bad thing. Okay, so let's look at a bit more of an advanced solution. Like we basically want to build like a web service to reverse strings, right? And the problem with reversing strings is how do you send the string to our application? I mean, you could just like add a string here in the body, but like then we would sort of, if we do that, we have the request reading here. But what if people want to reverse like a very, very long string? And of course you're paying like a few cents per request. So we don't want to read the entire body of the request before we do the authentication and make sure you're allowed to reverse strings. So yeah, this is a bit of a no-go. I mean, in that case it would look like this. You would read the request and you would reverse the body. But the problem is you're doing like a lot of reading here, and you're sort of like wasting your Amazon cycles, Amazon credits. You want to authenticate people first. So what you really want to do is sort of, you want to read like the header of the request, and then based on what the path is, or like what the authentication is, then you decide whether or not you want to read the body. Which is one of the examples, like it's sort of like hard to model this in pure code, or like a bit harder because you sort of like don't really know what sort of I/O you're going to do, is how I would put it. So this could be like a solution for that problem, right? Like what we're going to do is we're not going to have the body here, we're going to wait, but we're going to have another sort of like response type which says, instead of returning like a normal response, I'm going to return like a read body thing. And you sort of like, that has a function, and you will sort of like feed in the body there, and then you get the response. So in this case, you would sort of like have like a two-step process. In that case, it would look like this, for example. If you have like this path, what you do is you return this read body thing, which will then get the body passed in later, of course if the authentication is correct, and then you take that body to return the 200, right? So this is sort of like one way you can abstract out the pure logic from the I/O riddled code. Of course you need then some more like handling code, like what we call an interpreter often for that, and then in that case, you still need to sort of like decide what to do with the responses. Like if it's a 200, you want to just send it. Then the 400, you want to just error and like crash your entire application. If you have a read body, you want to then read like the entire body, which can be big, but like we assume that here we've already authenticated, and then you run again. So f of body will return a second response. So which is like the thing here. So if we feed the actual body to this function here, it will be put in this place, and we reverse it, and we'll finally get like the 200 here, which is in turn fed to run, and then you send off the response. So this is like a way you can do these kind of things. There's often like sort of like a degree, like how far you want to go in making things pure. Like this is actually like these sort of like interpreter patterns are like a good example of what we call like free monads. So which is this type. The way you would do that is instead of having like the responses and then the sort of like the special response body which reads some I/O, you would have like two types. You would have like the response type, which just contains like what you consider sort of like the final response of the application, and then you can have like some sort of like what we call handler functor, which has the read body. In here you can do more sort of things, which will be like, the trick is that this will be executed by an interpreter. So for example, we have our read body here. Now it takes a string, but when it returns, oh, this code is actually, the F shouldn't be here, actually. So I think this code is incorrect, yeah, because then you have the free monad of this handler, and it all becomes like a bit more complicated, but also a bit nicer. You can define like nice things like get body, which just call like read body with return, and you wrap that in a free monad. Or you can have like, for example, OK, which just returns the 200, and then you have these handlers here, which you can use in like perfectly pure code. Like this makes this pure code. You can look at what's the request path, then you can get the body, and you can send like OK 200, and this is still just handler. So this is perfectly pure code, and then you can pass this to some kind of interpreter, which hasn't changed much. Like the only difference is that we now have these free wrappers here, and you sort of like do whatever you want. And here you read the body and you call your function on the body. Yeah, this leads me into the next mistake. Are there any questions for the previous part? Or? Okay. So this sort of leads me into the next sort of mistake you can make. It's very easy to talk about these sort of like all these things people come up with, like free monads. Like in the previous case, I still think it's a good idea to design it that way. But you can go as far as you want. This is a famous example from the Haskell wiki, which like I have no idea what it does, but it's supposedly useful. And so the big thing is like, this is super subjective, and it's sort of like you and your team who sort of like decides what level of abstraction you use. But in Haskell, it's very easy to get to like an overly complicated code base. Like for example, if we look at this relatively easy function, it's easy to understand what it does, right? Like you have some sort of like get property, which returns like left with an error or right with something else. Like if it's okay, you want to show, oh, it should be v. Yeah, so this is like an easy function. Then you can also write it like this. You flip get property, because this function takes the argument first, and then you call either in like a point-free way, and with like either fail or return after show. Like this is very, very subjective which version is better, right? Like I think, like for me, I think this one is easier to read. I'm not super sure, because like flip is very hard to read for me. The either pattern is fairly common, but like this sort of code you see often throughout code base with like maybe even a few more flips in there. And my point is that it's like super subjective, and I think the main takeaway from this is that you should focus on like, can I read the code, and like, can other people from my team read the code above anything else? You can make some rules about it, but it's a very, very hard problem. Like how far you want to go in this sort of like abstraction. I think you should just focus on putting like readability and like how easy is it to reason about the code. Put those two things first. Okay, so that's also overdoing abstraction is an easy mistake to make. Like I remember at some point when I was just learning Haskell, there's this tool which allows you to convert code to point-free code, and I was trying to use that once in a while, and sometimes I came up with these sort of like really compose after compose over compose, and sometimes it's fun to do that, but I don't do that anymore. Okay, a similar mistake you can make is premature abstraction. Yeah, let's start with an example. So Haskell is one of the oldest things I've written, and one of the things I did there, which now like I consider a premature abstraction, is you have Haskell like reads a bunch of files from the file system, and you sort of like want to know like list me these files or list me these files. So I came up with this sort of like complicated abstraction called like a resource provider, which sort of abstracts away the file system. Like it's a bit maybe easier to use, and the idea was if I write it like that, then maybe later if I want to replace it by a database, it will be easier because you can still use some sort of resource provider. However, like some functions that use the resource provider still sort of like relied very hard on like the behavior of the file system, so they sort of like knew what was going on underneath, right? And then I had to like expose like more and more functionality from the file system, like get the modification time, but then you also want like the access time, and at some point you're just wrapping around like something which isn't really a proper thing, and then like of course it never got like database support. So these are some like signs of premature abstractions. Like especially the first one, if there's 0 or even just one instance of your abstraction, it's probably a bit premature. Then if you have this abstraction, but you feel like you're working or like trying to work around the restrictions of that abstraction a lot, it's also a pretty bad sign. Or like you make an assumption like that the abstraction doesn't provide. Like for example, for a monad you have some laws, but you're sort of like making this assumption, I can actually do this here, like it's not really documented, but I know how it works, so it's going to turn out fine. Or yeah, if like your abstractions are too general, too abstract. Like another, yeah, this is not really correct because it wasn't really designed like that, but it could be considered an instance of a premature abstraction. Like, for example, you recognize this pattern everywhere, you have this parser, and you have this thing called I/O, and they all like form this sort of like pattern together, right? Where you can sort of like return things and bind or join, like combine things together, and like this I/O thing and this parser thing also have this, and this either thing also have like this property. You can also fail them, so you can just like give a string and then it gives you this result. But in that case, it's also like a premature abstraction because you haven't realized that this doesn't really belong here as much as the other two, right? And I think in Haskell this, precisely because like Haskell is such like a good language to write, you can abstract over pretty much anything, and I think that makes it sort of like easier to go into the wrong direction, right? So you're writing some code and you think like, this looks like something common, and like, you know, like after you finish like this sort of like this handler, you're going to write some more code and it's going to be about the same thing, so you think, maybe I shouldn't write the same thing twice, right? That's what they say. So you sort of like start abstracting things out before you even finish the first one, and then you have like this abstract thing, you implement this first one on top of that abstract thing, then you start on the second one, but you feel like the abstraction layer you write it's not completely right, so you add a few more parameters to it, and like this is very, very sort of like easy to get into, to go into this alley with Haskell. And yeah, like for me, what I'm doing now to avoid this is whenever I think this, like I think of like all the times where I went wrong before, And then I say like, I'm just gonna write the code, and I wait and I write the handle like 3 or 4 times, even just by like copy pasting code and then like making a new note, like see if you can abstract this later or something. And then sort of like when you sort of like really see the entire pattern, and when you've sort of like written it a few times, like at that point, then it's often easier to actually capture the right abstraction. That's it for the mistakes I came up with. So thank you for listening. If there are any questions, feel free to ask. Yeah.
Do you have references for the premature abstraction, like something you can cite?
No. Anecdotal evidence, as you say.
Yeah, I was hoping for more like something which can...
I don't think there's ever been like proper research on that. But I think it makes sense, like the easier it is to make like an abstraction in a language, also like the more often you're going to make the wrong abstraction. It seems like there's some correlation with it.
No, it's obvious, but it's like still would be nice to have a...
Yeah.
What is your take on type classes?
Like they're a nice feature to have.
To me, I mean, if you talk about premature abstraction, is that I remember all the times I thought, oh, there's this type, I need to introduce a type class.
Yeah.
And a bit later, week or two, I find like, nah, it doesn't really work.
Yeah.
So nowadays, it's also a type class. I rather have 10 instances beforehand written out and named explicitly until I really go for a type class, and even then I'm sort of wary of introducing them.
Yeah, I agree, because like I think it's a bit the same as like with introducing higher order functions. Like it's sort of like a very similar thing to do, and like in the way of like premature abstractions, except like type classes are like even more expensive, because if you start doing that, you often end up with like these new type wrappers to provide like the instance. So yeah, they're a nice tool, but like I think I'm using them less and less actually. The more Haskell I write.
Yeah, I'd say the same. It's like, to me, what I see, one of the mistakes that for intermediate Haskells is like, I learned about type classes and they're Haskell's tools for abstraction.
Yeah.
And they tend to forget that actually you have higher order functions, and type class is actually just a way to get the compiler to write code for you.
Yeah, and I think like most type classes you need are already on Hackage.
Yeah.
Like, or in base even.
Have you ever felt like you did abstraction through as compression? So like, I wrote this code twice, I'm going to refactor it into a function even though it's not a coherent unit. I think that can also happen to some people, that they say, I mean, it's not very Haskell specific, but I don't want to write this code twice, so I'm going to make up a function, but then it's very difficult to reuse that function because it really only makes sense in small and not specific.
So I think I do that sometimes. Like, but I think it's fine if you do it like in sort of like rare clauses or something, or like if you do it like very locally, right? But yeah, you don't want then to sort of like, I think maybe even like within a module it's fine to introduce like these little helpers if the module isn't too big. But you, at that case, sort of like it's sort of like a leaky abstraction or a pretty bad abstraction, so you want to make sure other people don't use it basically. Okay, thank you all for listening.
Thanks again for the talk, Jasper. There's just a small announcement to be done. I mean, obviously there will be another talk next month. There's also, it's very likely that we'll have a Surihack again this year. Date is not fully confirmed. Tentative is July, but you'll hear more sort of in the next month. And then also there's sort of, one of the reasons why I've been organizing this meetup for a long time now is because I want to make sure that there are more Haskell jobs in Zurich and that will be ready. And so I'm going to allow myself to use this venue also to announce that actually currently the company I'm working at, 11's Digital Finance AG, is hiring Haskell programmers. So if any of you are interested, you can find our job posting on Reddit. I've just put it online today, or talk to me afterwards. So yeah, otherwise we're heading over to probably the hot pasta for a beer for the guys who want.